Hey there, folks. Tonic here. So I wanted to present my project called NuTonic, and specifically what it does is that it predicts the changes in Earth observation images based on a combination of two AIs, which is TerraTorch, TerraMind's TIM, Thinking in Modalities, plus Liquid AI's LFMVL, 450M models, and combining the two insights together in order to not only say what we are seeing in terms of static Earth observation images, but being able to predict the temporal change of what we might see. So why is that important? Basically, the intuition is that we're taking a lot of images in outer space. These are very fat images, and it takes a heck of a long time to get them to Earth, where we can analyze them based on very well-known algorithms that we've been using for, let's say, decades. But the problem is, once we observe an issue or an incident, it's already too late. So what I wanted to bring to the table was, instead of assessing what's the current situation, and by the time that we give the information to the right people, it's already dated, what we can do is predict what the evolution will be. So let's get into context. It's always about nature conservation and saving the planet, to be honest with you. So if you're observing, for example, human activity in natural reserves, usually you can predict that there will be increased activity. So based on the fact that there didn't used to be activity, now there is, but it's very small, you can identify that. But it's not really that important to the analyst, and it's not really important to the folks that are responding to it, because what they need to know is this human activity something expected, or is this something that we're expecting to increase, for example, in protected natural reserves? A high traffic waterway, like, for example, San Francisco Bay, it's okay to see boats there. A protected marine reserve in Patagonia, if you're starting to see boats coming in, that's illegal fishing. If you're seeing a couple of dwellings in a natural reserves in the mountains, maybe that's fine. But if you're seeing increased human activity in protected natural reserves in the mountains, well, that's illegal mining. So the point is to be able to figure all that out before it happens, because by the time you're aware of it and need to respond, it'll be too late if you didn't predict it early enough. So how does it work? Well, a user selects an image, and then we use a combination of these predicted models specialized in Earth observation called TerraMind, and we add it and inject it into a specially fine-tuned vision model. All right, we're back. So I'm just running the game using the source build command that is provided in the README. Yeah, so this, I'll get all this in post, but basically it's just running now. Okay, and where is it? Here it is. So this is the interface here. I made a game about it because I didn't want to throw away all my data, but we're not going to really focus on like this game. But I just wanted to show you, there's like leaderboards, and you can play on a map, and then it gives you like a reference still here, and you have to like figure out where this reference still comes from. Maybe not the best example for a demo, but this is not supposed to be my demo. So basically, you're like, hey, could it be here? And then you can add your guess, submit a guess, and in here you can show where so you're basically playing against AI. Anyway, we're going to focus on this. We're going to focus on this. So this is where the action happens on the Pro tab. The Pro tab brings together this entire system where it calls the TerraMind TerraTorch Thinking in Modalities model together with the fine-tuned LFM model that I fine-tuned in order to make them work together on your device. So let's just select something. This is not the best demo I've ever done, probably. But let's say we select this area. What can we say about Los Angeles Bay/Harbor? Probably we're going to see a lot of boats. So I have all these mini apps that basically you can use: detecting fire, detecting vessels, changing land use, flood prediction, and of course the brief composer, which kind of puts it all together in an analytical summary. So how does this all work? It actually makes calls to external servers, so not everything is on device. I have to be honest with you. That's because the TIM model, I couldn't fit it on a WASM edge for many reasons, but mostly because I cannot launch by myself into a huge integration project on a Torch fork, and then put it on a cell phone. But the good news is this actually does run on your cell phone. So the Liquid AI LFM model actually does work on your cell phone. Right now, what we're doing is we're collecting all the data that we need to make these predictions. It's gonna take a while. I'm gonna get most of this in post, I guess, and we'll see. We'll see. There we go. So right now it's got a lot of the input data it needs, and there it is. It's going. I'll get this in post, sorry, folks, but it does take the time it takes. We're running multiple runs of these heavy models. Heavy in a sense. There's different sizes for TIM and different sizes for LFMVL, but we're using the smallest possible size of LFMVL, 450M, and we're using the largest possible TIM model. So it's just running all the little mini apps. Actually, you can access all the mini apps from here, so definitely check it out when you're checking it out yourself. And once we have all the evidence we need, when you test it, you don't have to test all the mini apps, but I wanted to. So now we can run it on device analysis. So let's check it out. You can see it downloading the model there. Ooh, yes. Okay, great. And crashed. Great, fantastic. So we're really getting the live demo experience right now. I had to basically, navigate this. So I added these coordinates. This is a new demo that I had to make just now for this presentation. I added the coordinates for San Francisco Bay near the Golden Gate Bridge, modified the zoom and changed it to, well, let's try the brief. I'll just show you how it looks right now. We enable TIM, add the parameters. Let's go with full stack. And yeah, so I just want to show you how it looks now. Let's run the job. Oops, not this, here. So this demo I had to make real quick just to because the KML kind of went haywire on my computer. But so let's just check the brief. This is it here. We've got a lot to cover, so I'm gonna move on. Hey there, folks. So take 24. I couldn't leave this without talking about data training and evaluation, which was kind of the main deal. So let's just remember what this is about. This is what we're doing. So we're using the user inputs lat longs. We collect the satellite imagery. Based on this, we send it to the Teramind prediction model and VLM. But so the Teramind prediction model returns its predictions, and we inject it with the original images back to the VLM inference, which then, based on its training, produces the bounding boxes and captions, which we then write on the images and return the images. It's really that simple. So this was our training run, and so we made all this data, and we made this training run, and we see the eval loss going down, and that's great. So in our data set, we have the train set, we have the val set, and we have the test set. So this is all from my data. And where does my data even come from? So let's check out an example of it. So this is what an example of it looks like. You have the system prompt, you have the user input that inputs one image, and then you have outputs here. We have a lot of different data. Actually, I made one of the largest data sets for this project in this that's been shared on Hugging Face. There's someone I look up to, Julien Blanchon. He's made one a few years ago. So the golden standard until today has been the lava model, actually. That's what we were always using to caption these things. But that's not all what I did. So how do we get the answers? This is all procedurally created. That means that I think that we have all the algorithms we need. We know how to process these imageries, and we know how to evaluate the outputs of these algorithms. And that's what I did. So I started off with a seed data set that was a Google Street View data set. Okay, and the Google Street View data set is great because this guy, he had spaced it out, and so it covered the whole planet. And so what I did was I took each one of those POIs, I jittered it, so that creates some kind of rigor in the post train. So that's what we're doing here. And then so what do? We take these stack images, we post process them. For example, a process called rasterization, and then based on the stack metadata, the rasterization, we know the lat longs, so we can then use third-party services, for example, Google, to enhance the metadata and then do our calculations based on that. That means that we know what we're doing, and our data, we know that the results are high quality, and therefore when we fine-tune with it, we know that we're at least fine-tuning with the correct answer. But this evaluation is based on basically my training set, or at least a subset of my training set. So that means that the eval is only looking at images that are basically identical to what I've trained on, and that's great to show success, but it's not great to show generalization. It's not convincing. So what did I do? I took Patagonia as an evaluation scenario. Patagonia is the perfect place because it has everything I need: forests, lakes, marine reserves. It has glaciers. Recently, it has fires. It has floods, and most importantly, it has no street view points of interest because presumably there are no roads in these natural reserves, right? So if I can prove that it works in Patagonia, then it's generalized. And the results that we got say yes. So that was actually a surprise. The way I evaluated I went a little bit too far in the evaluation, but basically we're looking at captions quality, bounding boxes labels quality. We're looking at, are the bounding boxes actually correct based on our golden answers? Is the model responding in the way that we trained it to respond in, and so on. All that is weighted. The evaluation is quite configurable, so you can run it again. And this is what we found. We found that adding the temporal aspect to it helped both the base and the fine-tune. Moreover, we found that we could get the base from 0 to almost 3/4. We found that grounding increases, that faithfulness increases slightly, and that we're able to, in aggregate, have a better intelligence with our fine-tune than in the base model, which was kind of unexpected. So great news. It all worked out. And the point was that we wanted to demo this quite unique concept. I haven't seen it anywhere else, where you take a prediction model and you take an image model, and together you can have a prediction that makes sense for prioritizing earthbound response. So yes, we can see that there are people living in the natural reserve, but that's not so bad. There's unlimited amounts of instances where that's totally acceptable. What we're really looking for is, what's the directionality of the built area? So say in an area that had nothing, and now it has 3 spots. Well, with the prediction model and the vision model, now we can say this should be a priority because the evolution that we're expecting is increased built area in a protected area, natural reserve, right? So hey, let's go investigate and audit that part. Or maybe marine reserves. My Patagonia eval had no vessels, which is great. That's exactly what I was expecting since I was looking at marine reserves. But say now we're finding vessels in marine reserves. Well, that's curious. Let's check it out. And that's the point I was trying to make, that near real time is already too late. So we should look at what we're expecting in the future, and based on that prediction, prioritize earthbound response. So sorry, this is take 20. I have to go to take a train now, so I can't make another take, and I hope this one renders. Thanks for listening. Goodbye.